G'day and welcome to the series on exponential and log graphs. This video here will deal with exponential graphs and the next one will probably deal with log graphs. Now I'm going to use base E. Remember we looked at E the other lesson. E is Euler's number, approximately 2.71. I'm just going to use that because that's commonly what we use in Year 12. We could use any base, pair of 2, pair of 3, pair of 7.3 if we wanted to, but I'm going to use E just for all these examples. Now, the standard form, I think you guys have seen a bit of this sort of last year, so I'm not going to I'm going to assume a couple of things. Again, if you've got any problems, if you've got any questions, please let me know. So here's a standard form of an exponential graph. This is what the standard shape looks like. It gets close to the asymptote down here, and then as it gets further across to the right, it gets bigger and bigger. This is what we call exponential growth, and there's also exponential decay as well, which I can show you a bit later. Now it has an asymptote on this number here, the plus k, so that's where this asymptote is. For most of them it'll be y equals 0, but you can move the graph up and down. The dilations are the same. The a and the b affect the dilations. A from the y-axis, A from the x-axis, b from the y-axis. They also do the reflections as well, the same as what we've been doing in the other ones. So A is from the x-axis, B is from the y-axis, and H and K just move the graph up and down or left and right. So H moves it left to right, and K moves it up and down. For exponential graphs, we don't really notice the translation left and right, as I'll show you a little bit later. But we definitely can easily tell the translation up and down. So as I said before, the asymptote is at k. They have a domain of r. They always all real numbers. So negative infinity to positive infinity. So just to be clear, that's the same as this. Okay, or it's the same as negative infinity to positive infinity, like that. Okay, all of those three things there mean exactly the same thing. Real positive numbers is the range, so that one is just from 0 up to infinity. So you can do that and it doesn't touch 0, or you can go from 0 to infinity this way. Okay, let's get on to some of the graphs. Now the dilation, translation, reflections are exactly the same as every other graph. This is like the matrix moment that I was talking to you about last year, where you start to realize all graphs are the same. They're straightforward. So we've got our dilations. If A is less than 1, it's compressed, stretched. If from the y-axis, if B, B is a bit trickier because it's 1 divided by B, but it can be either compressed toward the y-axis or stretched away from the y-axis. The reflections, you can reflect it in the x-axis, which means that sort of flips horizontally. Or you can have it reflection in the y-axis if the negative is inside the power. We'll see that later on, but this would be e to the negative x. That would mean that the graph is flipped about the y-axis. We can also move it left and right, up or down, but really we'll just look at the left or right here. The only thing that it really changes is the y-intercept. That's the only noticeable change that we can see, unless you've got both graphs on the same axis. And we can also move it up and down, and this moving it up and down changes the y-asymptote. Okay, there's no x-asymptote for these graphs. So a couple of graphs just to show you. So for example here, this one has been moved to the left 2 units and moved up 1 unit. So the red one is the standard graph, and the black one is my new graph. Okay. As you can see, the new graph has been moved up 1 unit. And which means the asymptote has been moved up, so y equals 1 is now up there, and whereas the old graph actually cuts through that asymptote, because that's not the asymptote of the new graph, that's the asymptote of the new graph, not of the old graph. So therefore we can see that it's been moved up 1, but it's also been moved 2 to the left. We can't really tell the difference. I mean, really it's kind of this point over here is now this point over here, this point over here is now there is now there, but we can't really see that all that well. So basically for these graphs, all you need to do is put the y-asymptote in, and then put the y-asymptote, and then also put the y-intercept in as well. If it has x-intercepts, we put those in, but this one doesn't have any x-intercepts. Okay, let's move on to example 2. This one has been dilated by a half from the y-axis because the b is 2, and it's also been reflected in the x-axis. Okay, so this means that every x value has been multiplied by a half, which means that it's kind of squashed it in a little bit. So each of these points are now, was over here and now it's over there. This point was over there, now it's over there, but it's a little bit hard to kind of see. The only thing that's really noticeable for this one is that it's been reflected in the x-axis. Okay, the intercept is now -1 rather than 1. Okay, just two more examples for this one. We'll skipped it down too far. This one has been, again, I can't read that straight away, so I'm going to turn it into a form that I know, which is e to the negative x minus 3, and then minus 2. So I can tell you that this graph has been reflected in the y-axis, translated 3 units to the right and 2 units down. So I put my asymptote in at y equals 2, and I also translate it 3 units to the right. Now that is only going to affect the y-intercept, so I won't worry about that too much just yet. I'll just have to find the y-intercept. And the other thing is that it's been reflected in the x-axis, in the y-axis, sorry, which means instead of going from left, the bottom left to top right, it goes from top left to bottom right. Okay, this one is called exponential decay, okay, because it's getting smaller every single time. Okay. Example 4. Again, I don't know what that is, so I'm going to put it in a form that I like, which is -2e to the negative x plus 2. Okay, so then I can tell you that it's been dilated by 2 from the x-axis. It's been reflected in both axes, x and y, and it's also been translated 2 units up. Okay, so the first thing I do is I'll put my asymptote in, y equals 2, which is there, and then I can dilate it in both axes, which means instead of going from bottom left to top right, it switches in both axes, which means it ends up doing this. Okay, looks kind of similar to a log graph. It's not quite though, because log graphs have different asymptotes. And it's been moved 2 units up. Well, the only really way we can know that is by looking at the y-intercept. So chuck x as 0, and we end up getting that it goes through the origin of 0, 0. Okay, just a couple of unique cases that might occur. You don't have to know all this, but sometimes it can be a little bit helpful to know all the little tricks. So if you have the graph of y equals x plus, 2 to the power of x plus 2, I can turn that into 2 different things, because when you multiply the bases with the same, you end up getting, you add the powers together. So I can turn this 2 to the x plus 2 into 2 to the power of 2 multiplied by 2 to the power of x, which ends up being 4 times 2 to the power of x. Therefore, the graph of y equals 2 to the power of x plus 2 is exactly the same as y equals 4 to the power of, 4 times 2 to the power of x. So here, a translation actually ends up giving the same shape as the graph as a dilation does. Just one of those unique cases that can sometimes occur. Another little trick that can happen is that if you've got a reflection in the y-axis, now, using algebra, I can get 2 to the power of negative x into 1 over 2 to the power of x, just dropping it down and changing the sign, and that is the same as a half to the power of x. Therefore, the graph of y equals 2 to the power of negative x actually looks the same as y equals half to the power of x. So, when it's a half, or when you've got a fraction here, a number less than 1, then it's actually going to be exponential decay, which is the same as a reflection. Those two graphs look exactly the same. That can be a bit tricky. Ask me if you've got any questions about that. Otherwise, grab your CAS calculator out and start doing some things on that. This is, I think, what I mentioned before. If you change the base, the shape of the graph won't change. However, it will change the rate of growth or decay. So, for example, if I change that 2 to a 3, nothing would happen. The shape of the graph would look exactly the same. It's just it would be a steeper growth or a steeper decay, depending on what you've got. Generally speaking, if the base is greater than 1, the larger the base, larger the steepness, or larger the growth, or larger the decay. But if the base is between 0 and 1, it's the smaller base or smaller decay. So that's exponential graphs. I hope that's helpful, and the next video will be on log graphs. Thanks very much.